Obviously, a massive thank you to Jatin and Sagar for joining us this evening. A few words, a bit of background. For those of you that don't know me, my name is Barry Cranford. I'm the founder of the London Java community back in 2007. I also run RecWorks, which is a tech recruitment company with a long history of working with Java developers. So here at RecWorks, we've been on a mission for about the last 12 years to find ways that recruitment can be a force for good in the industry beyond just getting people jobs. And it all came about when I realized that we spent all day, every day as recruiters speaking to and connecting with people in the same market, always Java developers maybe moving into the area or CTOs that were hiring graduates and things. And I started wondering if we couldn't use that position at the heart of it all to do more good things. So that's really what we're trying to do, using our position as connectors to bring people together for career development, for learning, mentoring, all that kind of thing. So I like to find the ways that people have gone different directions with their careers and then try and help take that knowledge and pass it down to people that are earlier on in their career. So we also have a recruitment company, as I say, at the back end of it all, sort of more of the day job. And we run a mentor introduction service as well. So if anyone's interested in any of that, then please let me know afterwards or find me on LinkedIn. Anyway, on to this evening. So we have Jatin Bhadra joining us, who is a technology leader, an architect, consultant, and manager with a background in the financial services and commodity industry. He's also got a strong experience in agile, DevOps, and cloud-based system delivery, as well as Sagar Bijlwan, who is a team lead and development manager with Jatin, who also has strong exposure to a multitude of Java technologies. So I'll hand over to you guys.
Great. You can hear me well? Great. Thank you. Thanks, Barry, for giving an opportunity to come over here and share our experience in the journey that we have had, an interesting journey that we have had over last year and a bit running blockchain applications. So I'm going to start sharing my screens and we will kick it off. So give me a second whilst I set it up. Right. So if everything went well, you should be seeing my screen now with our what we are going to talk about today. Yeah.
That's it.
Cool. Yeah, great. Thank you. So we'll go through introduction, as in we will introduce what Vakt is, what we do at Vakt, how the company started, and what is the business problem domain that we are here to solve, and how blockchain becomes relevant to the business problem domain that we are going to solve. We will touch high-level architecture, so I'll cover first three aspects, and then I'll hand over to Sagar, who is going to talk about the application side, application architecture, the learnings and challenges that we have had with the current setup that we have and how we are addressing those. We'll touch a little bit around the monitoring and cost aspects of running blockchain style systems in cloud and how that presents its own little challenges in the test environments, etc. as well. And then we will open up for Q&A session. Barry, if you're still around, then during Q&A sessions, is it something that we can unmute the participants?
Yes, absolutely. Yeah, that's absolutely fine. You'll have full hosting ability, so yeah, you can go ahead and do that.
Okay. All right.
Also, great. Just to let you know, Jatin, you've got on the presenter view on here.
Oh, okay.
That we can see. Thanks, Yuri, for that.
So let me share it again and let me know if that works well.
Yes, that looks right.
Yeah.
Yeah.
Cool. Great. Thank you. So what is Vakt? So Vakt is a startup. It was started by a bunch of oil trading and oil explorer companies and banks. So essentially, what was happening is like these companies who are big oil majors, they trade oil with each other regularly. So a company may have extra oil, they may sell crude oil, whether it's refined oil, whether it's petrol or diesel, to another party, and they will call each other. They'll agree on the trades, and then they'll hand over that operations down to their operations team to get the logistics arranged for that trade to be delivered between the parties. Now, the age-old process was to send emails, faxes, telephone each other to organize all the activity around the trade agreement and then around the logistics of the trade. There was no centralized platform where that data can be held. And there is a good reason for not having centralized platform that was never built. Is because the nature of their business is very secretive. The margins in the businesses are well protected, and they want to make sure that all the trading activity, all the logistics activity is not really exposed to their disadvantage to any of their competitors, or for that matter, any centralized company doesn't hold too much information about the whole market to be in a position where they have got more knowledge about the market than the trading houses or the oil explorers themselves. So they were living with this problem for years and years and years. So what would happen is they would agree on a trade, or traders would agree on the trade on the phones. They would go back and get that details entered into their own IT systems. And then when it comes to a point of invoicing, or when it comes to points of actual delivery, at that point, they may find that they have a disagreement as to what was understood on the phone is not really exist on the systems, and that would lead to delays and ultimately affect their profits and bottom lines. And centralized platform presents its own challenges, where a company that gets all that data is suddenly having more knowledge of the market than the trading companies themselves. Um, then came the blockchain technology, the distributed ledger, especially around blockchain, where the companies realized that having distributed ledger means that the data can still be protected, and each company can still have a copy of the ledger with themselves, which means it is no longer centrally held data. And also the fact that it's immutable, it ensures that there is no tampering of that data once the data is returned to blockchain. So those are fundamental two key concepts of blockchain technology that these companies realized, and hence they started us, that is Vakt, to build this blockchain platform that allows them to now digitize all the communication that was happening over non-digital channels like emails and telephones and faxes. So the key point over here is that when we talk about blockchain, we don't talk about cryptos, we don't talk about mining, we don't really talk about tokens either. The technology that we use over here is the distributed ledger technology of blockchain to address the privacy and tamper evident concepts, tamper evident requirements that these companies have. So it's very important, and that's why I spent a little bit time explaining you the business problem and giving you the solution and explaining the solution why blockchain is used in this case. And it's definitely helps, because at one point in around 4 or 5 years back, blockchain and crypto was trending very high. But we have a genuine business use case that we are trying to address over here using distributed ledger technology. So this is just a recap of that same screen as to what a trade life cycle looks like. A trade is agreed, and then trade is entered into customers' own internal systems, and then a trade is recapped. So a trade, in case of not using Vakt, it would be basically exchanging emails that this is how I understand trade, and the other party would say this is how I understand trade. In case we start our journey from here, and this is where our platform comes in, that rather than them having to exchange that information via emails, they use Vakt as a platform which is underpinned by blockchain to do the trade recap. And then comes the sections around confirmation of those trades, and then arranging the logistics, which is where it comes to saying that here is a vessel, here is a ship, here is a barge that will come to collect the product and then to deliver the product to a particular terminal. And this inspector would come and inspect the product. And that's the whole pro module around logistics. And then comes invoicing data and settlements. So the two aspects which are in a different color, we don't get involved in those two aspects. The traders can continue doing their trading how they want. The ultimate payment can work through any payment processing system that they want, but everything in middle is what we are here to address, and of which some modules we have addressed and we have developed and are running live in production, especially around trade recap and logistics. So this is just the ecosystem aspect. So these are the customers that we work with. All of these are running critical systems and do require enterprise grade platform, which is what we will talk about in next few slides. But as I talked to you before, traders are our main investors and our main customers as well. So these are big companies like BP, Shell, and some pure trading houses like Gunvor and Mercuria. And then there is banks who are interested in trade finance aspects to finance those trades. Terminal companies is where the products are held, and then ultimately facilities are there at the terminals to allow for shipment of those products. Inspectors would go and verify the quality of the products, and then brokers and ship owners are the other parties who help out in making sure that the product gets delivered on time. So the three key concepts that we talked about that Vakt we promise, and this is where we will touch into when we talk about the architectures, which is a permanent logging of transaction. That means the transactions that go are always immutable and are temper evident. The privacy aspect of transaction we will touch into and how we use blockchain to ensure privacy. And enterprise grade, as you saw, that the customers that we work with are big customers, and it's ultimately time critical that the deliveries and all the aspects around delivery communication happens on time. So the SLAs that we have to maintain are have to be of the enterprise grade. So let's touch a little bit on the privacy aspect of the transaction. So a box standard Ethereum blockchain distributed ledger, which is if it were to be used, then all the transactions that are flown into Ethereum are available to the whole network. So there is no such thing as privacy, although the transactions are encrypted and the signature of the transaction doesn't really tell you who the owner or who is the what's the right word, whose signature it is. However, still all the transactions that flow through the network are pretty open, and that's why it's distributed, and that's why it's open. However, the network that we build is not an open network. Not anyone and everyone can just suddenly decide that they are going to participate in the network. Our network is a permissioned private network. There is an onboarding process that allows the customer to join the network. And once the customer has joined the network, they remain in the network until such point where they may want to stop using the network. So that's one aspect of privacy that keeps the transactions and the network private. And then there is a second aspect that we touched on before, which is what if a transaction is done between two parties? Does the copy of that transaction, although encrypted, is available to the whole network? The answer is no. We use a quorum technology that ensures that if a transaction between two parties can be marked as private, or for that matter, multiple parties can be marked as private, and which point the data for that transaction is encrypted and the data resides only on the participants who are part of that private transaction and is not distributed to all the parties. So that's an extra layer of privacy that quorum technology offers. And that's what we use as part of our blockchain network that we build for our customers. So let's talk about that over here. We use the term pod. If you think pod, then pod is essentially a combination of services that runs the application. Here, what I'm representing is multiple pods that are part of a network. Each of this pod is a pod of a given customer. And there are a bunch of services that run in that pod. If you go into the details of what runs in the pod, then at the very bottom, that is the persistent layer where we persist all the transactions, is Quorum, which is the distributed ledger technology that we have in the pod. To access pod, we have a layer of Java, that is the Java API that runs over here that accesses Quorum. And then to allow our customers to process the transaction, that is to enter the transaction into the network, we have a React front end. So this is where an operator, a human user at our customer's end, can enter the transaction using a React front end, which flows through Java API and goes down and writes the transaction to a blockchain network. Obviously, we don't really want our customers to be sitting over there and entering the data into our platform as a manual users, because they have to do exactly same in their own ETRM systems. That is where the messaging infrastructure comes into play. So using messaging infrastructure, our customers build the gateways that will allow them to flow those transactions from their ETRM systems into Vakt, and thus then communicate out to their counterparties. There is a layer of protection, obviously, the identity management, which is done using Keycloak, and then comes supporting services around monitoring, logging, and secret management. There is a local database cache as well, and we will explain to you what this database cache is and how we use that to optimize certain operations. So I'm going to go back one slide. Over here, we saw that there are multiple arrows flowing through between customer's pod. And this is where the quorum communication comes into play. This is where blockchain communication comes into play. So in this customer's pod, a transaction would come in through a human user or through their systems integrated via messaging infrastructure. As soon as a transaction comes in, a transaction would be marked for a given counterparty or for a given combination of counterparty. Let's take a very simple example of a buy and a sell. A customer pod A and a customer pod B may have a buy and a sell. So when a transaction is entered by customer pod A to say, I want to buy something from customer pod B, or I have a transaction that is a buy transaction, it's one and the same thing, then that at quorum level, the transaction is exchanged between these two. There's a quorum transaction that happens over here. That means a buy side is available to both pods and that data resides on those pods. So the key message over here is each of these pods are completely separate, so running in a completely separate cloud network. And the only mechanism that they use to communicate between themselves is quorum, that's blockchain, thus making sure that all the communication that happens is always recorded, always timestamped, is always tamper evident, and is always immutable. So going to the last one over here. Okay, sorry to jump around too much. The pod that I talked about, these are all customers pods. There is one pod that is called as Vakt pod. Now, this pod doesn't have any quorum node. It doesn't participate on the blockchain network. This is essentially a service provider node. The job of this pod is just to provide some essential services that are required for these customer pods to work, of which one is reference data. Uh, as we are standardizing the communication that happens between all of these customers, reference data is a key aspect to allow all the parties to talk in the same language. Otherwise, we have a challenge where one customer may call diesel, another may call it as USD or something like that. So we use this pod for one of the key services, which is reference data. So this holds master reference data. And whenever there is any update, this is the location where the update to reference data happens. And then that reference data is distributed to all the pods. And that is done using messaging infrastructure. There are a couple of other items that go over here as well, which is what this slide is trying to say. There is reference data, then there are some shared storage. So when customer wants to share documents with each other, then that's also something that goes over here. And communication to trade finance partners also happens through this pod. But for simplicity, you may think that this is essentially to make sure that reference data is distributed to all the pods is the purpose of that Vakt pod. And other key concept is the promise, which is Vakt doesn't participate in quorum transaction. Vakt has got no visibility of quorum transaction, means that there is no quorum node that runs on that Vakt pod. So hopefully that gave you a high-level picture of what Vakt does, how we run, what is a pod, what is a quorum's purpose. And now I'm going to hand over to Sagar, who is going to walk through some application aspects.
Hello all. Jatin, should I request you the remote control because you're sharing?
Sure.
Yeah, I'm just gonna request it just so that it's easy for me to navigate. Hey, hi again. So Jatin has covered very nicely the basic architecture. He's made my job easier. So just to let you know that we all understand the advantages of blockchains. We all know what it is used for. But for our purpose, just to reiterate, so we use the blockchain because data is immutable. And since we use the private transaction, so it's visible to only the involved parties in the transaction. So to give you an example, a long blockchain, we can visualize a long blockchain as a long list of blocks with each block containing some data. So we use blockchain solution called Quorum, as Jatin mentioned, Ethereum-based solution called Quorum. It's rather straightforward to store the data without doing much thinking. You just call the provided APIs, and here you go, the data is stored in the blocks. However, when it comes to read the data that client has requested, let's say client say, I want some data that I stored in the blockchain, it's not trivial at all. Why? We'll see that now. So what's the challenge in that? Challenge is to map the business requirement to the technical domain. So let's, as it's mentioned in the slide, so we have a mapping request. So mapping request is, for illustrate, let's say we have an example of an online bank application, a bank that is based on the blockchain, okay? So we have provided an application where user can create account, deposit, transfer via application, and it's a long chain of events that a user can put your action on the blockchain. Now, after a few operations, user want to access the latest balance. So if you look at the example here, so user has created his account 123 and deposited $100 into account 123. Now, another user created account 456, and at the same time, the next operation of the blocks, our user A has taken $5 from account 123. Now, the latest balance on account 123 is $95, which is when user X wants to access this request, he wants to know what is the latest balance of 123. Now, this is a very classic example of finding the latest balance from an array list or linked list or whatever you want to call it. But that has to happen, one has to find out where the last operation regarding 123 account happened. And this is not trivial at all because you have to go and search it. This is a rather long list of blocks. It's also a business problem, which we have to understand. It's not just your single linked list of strings in Java. It's a linked list of the block. Okay, so we can see this clearly a problem here. And if you go to challenge 2, the challenge 2 in this long list of block, the data is not stored like I mentioned in the previous slide. It's not like our latest balance. It's data privacy has been trained by having the data in the encrypted state. So this is how a general data in the blockchain would look like. So what you have to do is you have to read the block, find the appropriate block, read the block, and decrypt the data. So now, once you've decrypted the data, now it will give you your normal data that you will serve the clients. It's a JSON string where you say account number 123, current balance is 95. Now, if someone in Vakt, our customers, those are trading, they have to read their data. So let's say a customer wants to say, from my blockchain, I've created a trade with party B for the month of December. Tell me what happened in that trade. What was the last date of the trade? So you could imagine a customer can push thousands of trade, and you have to go through and look into that blockchain of the customer, and you have to identify the block, relevant block, and then decrypt the block, and then give the response back to the customer. It's a rather hefty operation, so it's not as per the industry standard. So while the customer is waiting for the response, you might as well go and grab some snacks and come back, and there you go. So as Jatin mentioned, it's an enterprise grade system, so we have to meet our SLAs to give the response in the allowed time, so that our customer, making the customer user experience rather a smooth journey rather than making them wait for long operations. So, sorry, oh, oops. I think I'm missing Jatin, if you could.
Do you want to, let me go back a few slides.
Yeah, please, if you could go back. I think this close control is not what I wanted to show.
Is this
not
the
this.
one?
No, please, if you could go back, please go back a little bit further. Yeah, if you just next slide. So yeah, that's the one. So how do, generally, in Vakt, how do we find out what is inside the block? So what we do is we use a Go Ethereum standalone client called Git. So using the command line methods, we calculate, we find out what's inside the block. So what we do is find the block number. In most of the cases, when we are debugging the application, is the last block of the blockchain for a particular client. In the next step, what we get the transaction data of the block. So if you could see from the transaction block, we get a hash of the block. This is the transaction hash. Now we get it transaction hash, so we call transaction receipt using this hash that we obtained from the last step. So what does it produce? It produces a long list, a long string of the encrypted data. So what we do is we convert this hexadecimal string using some string converter utility, and then it produces an actual readable data that client has actually wanted to see. So now you could see there are chain and sequence of steps that we need to follow to serve a read request to a customer, which is definitely not performant. So how do we do it? We used an industry-wide pattern called CQRS. I'm sure most of you are aware of what CQRS is, but those who are not, just to bring everyone on the same page. So CQRS is command query responsibility segregation. It just, to simply put it, just we can have two models, one for read and one for write. Just to give you an example of how it works. So imagine we have an online store where a user can order any item from the online. So if we go with the modern architecture where there are multiple microservices, so there might be a user account service where user can maintain their accounts. There's an order service, user can place a service. There could be a payment service. There could be a delivery service. And when these are all microservices, so given the purity of the sys microservice system, they will have their own individual databases. So possibly a relational database like MySQL, Postgres, and others. And what the service do, they write to their own individual database using a domain specific write model and their domain can be mildly different from each other. They don't need to be exactly in the same domain. So now that is the read part. Now when we have a page in the UI where all the services need to be queried to load the page, you might ask what that page is. That page might be a user historical data orders. So where you could see all the historical data for a user, you need to access the order service, payment service, how the user paid for that order, delivery service, how that order was delivered to the user. So all these services might need to be carried to load that page. Now, you can see here, our read model has to go and encompass all these different DBs to actually present, to load that page. And if you take the case of the monoliths, you could simply map it to joining multiple tables to actually serve the page. So what we do is, to solve the problem of having a performant read, what we can do is we can introduce a data model that is very different to a write model. And most of the cases, in this case, preferably what we do is bring a document database like MongoDB and start dumping the data in the format that you want to present to the user. So in which case now what happens is we have solved the complication of encompassing multiple services and databases and then presenting read on the runtime, rather than we have presented a model, a database which already has the data in the format that user wants to see, and you just have to query the database and here you go. And in monoliths, I think if I having a comparison, then monoliths, we can use the materialized view to perform the same, to overcome the join complexity. So what is the good points of using CQRS? Obviously, we have performance rights, and our read and write models, they are completely separate from each other, and hence they can be evolved individually. And what are not so good points? Well, obviously, we have now maintained two databases. So there's added complexity. And since the data can be duplicated, because we have one database for the read and one for the write, and same data is duplicated across. So that's kind of a duplication that we have inculcated in the system. So how did we use CQRS? That was a little bit of 101 on CQRS. So how did Vakt use the CQRS in our system to overcome the challenges that we presented in the previous slides? So what we do is we have sell this idea of the customer that their data is immutable. So no way we are going to change our write model. So our write model is the persistent layer is blockchain. That is our source of truth. But what we can do is, from the data that we are writing to the blockchain, we can copy or mirror the same data in the conventional format in a database. So our query model would be a CRUD data model. If we start storing in a conventional database, let's say Postgres or MySQL, we would solve the problem of having to find the latest block and then decrypting the data and presenting to the user. So we decided to maintain a mirror image of a blockchain in a database. And how did we do that? We can look into this slide. So this is just a model. So it's not exactly what we have as the business request in the Vakt, but it's just a model to illustrate the problem, because if I talk about our business model, probably that would be too much. But in this case, probably it's very simple. We have two parties involved, A and B. So let's say it's, again, same banking application where A and B are the two clients, and A, they're involved in a private transaction where A is sending $100 to B. It's transfer of an operation of the bank. So what happened is we know that A is the initiator of the transaction and B is the receiver of the transaction. And there are other parties involved, but because it's a private transaction, they're not involved in this transaction. So as Jatin briefly mentioned, we have pods. So again, just to say, the pods are, you can see a customer's or a client's system view of the whole system. So they have, each and every customer client have the pods, and they have the same set of services in those pods. So they have some application code, some services, database, and their own individual blockchain. So just to reiterate, to bring everyone to the same page. So this is a system view of a customer A's pod, and exactly we will have the same view for customer B but that's not shown here for the sake of brevity because it would be otherwise a large diagram. So let's just focus on the A system. So A wants to send $100 to B. So to start the process, A will send, let's say it's a REST-based application. A will send a post request in its own system to say, I want to transfer $100 to B. Now application code will receive the request and will start processing it. So usual pre-processing steps like validation and account checking and everything else will happen here. Given that all that passes, all that is good, now the request needs to go inside quorum because that's our persistent store. So how do we application code publish that into quorum? We use Web3j library to publish the data, or we say in this case in blockchain terminology we call smart contracts in the blockchain. So just a brief overview, Web3j is a Java library that aids in integrating application code with Ethereum blockchain. Just to set the page right, that's what we use. It's kind of a wrapper that kind of handles all the requests from Java to quorum and vice versa. Now, once we start this request to send it to the quorum, so A's transaction is now converted into a block in the quorum in this blockchain. Once the block has been added, what happens is our quorum, it emits events. Now it emits events to all the parties that are involved in the transaction. So A is the sender, so definitely A will get the event that the block has been added to the blockchain, and B is the receiver. So B will also get an event that a block has been added in the blockchain where he is one of the parties of the transaction. Other parties will not get that. So in this case, the event will be emitted to A and B both. Now we could have stopped here if we wanted to make quorum as our read request, and then we would initiate a request from this, and it would have again gone to the application code. It would have queried the quorum, and there would be again this hefty operation where we have to find the relevant block and return it back. So we wanted to avoid it. So what we do is we said, okay, we want to mirror a database. In our case, it's a Postgres. So what we have event listener inside our application code that listens to the quorum events. And only, as I said, only emits to the pods or the system that are involved in the transaction. So based on the type of event, in this case, it would be, let's say, for example, a transfer event where money is being transferred from A account to B accounts. Event listener would trigger a spatial set of services in our application code. We call those services event processors in our pod. So for transfer fund event, probably we will call transfer fund event processor. And what does that event processor does? It gets the data from the quorum, because when the quorum emits events, we also get the payload back that has been added to the quorum. It kind of receives the data, and it creates in a format using obviously some Hibernate library, Hibernate entity classes. It kind of start putting the data into the database. So now what we have done, the same data which is inside quorum is now residing in the database, but now it's in the format of relational models rather than blocks, encrypted blocks in the quorum. So now A's event processor would trigger, and it would calculate, oh, A has transferred amount 100 from his own account. So now A's account would be less than 100 and B's account would be more than 100 in its own database. So now if A has to inquire about the latest balance of his account, A would simply issue a read request to the application code. Application code would go and directly call the database, and it's all hunky-dory, just like in the old days. So yeah, we have made our system kind of more read performant here. So now again, good points and bad points of, or rather I should say not so good points, because we didn't, that's how I want to say it. So good points of having this approach. Well, we solved the complication, performant read operation. Now we can have the no complication involved in reading the data, performant read operation. Also, we have a backup storage alongside blockchain. And in this case, also we have an added advantage, just like an event store. If database is corrupted or lost somehow, we can replay those events from the quorum and build our database again. So we have kind of a backup storage in our system as well. Well, again, not so good point. So not so good point because since we're using CQRS, so we will inherit all the bad points of CQRS because we have added complexity. We have to maintain our two data models now, one read model for the database and for write model for the blockchain. Also, there's another issue. So in case we need to update our smart contracts, the smart contract that reside inside the block. So there's an overhead of editing the event processors in application. And one, we have to edit in such a way that it's also backward compatible. In case it's not possible that we can't maintain the backward compatible approach, then we would have to maintain two versions of the event processors. So that's probably not so good points. So yeah, this is how we tackle the issue of performant read operations. And alongside these, so this is just a basic overview of how we overcome one of the technical challenge that we had in providing an enterprise-grade platform to our customers. Whilst running 1 year in the production, we also have found some challenges in our daily development and the inherent flaws in our architecture we noticed. So what are those is our code base is purely monolith. Now, I know many people can raise the eyebrows now, say, why in this day and age you have a monolith? It was an architectural decision in the beginning. Maybe we had the urgency to provide a working product to the clients in a reasonable amount of time. Maybe, you know, untrodden path of blockchain and given business domains were too complex and we wouldn't want to add extra complexity to having microservices in the beginning. So we decided to go with the old friend monolith. Now, it may all have made sense in the beginning, but since then, Vakt has grown in terms of features we are providing to our customers. We have various markets that Vakt has started to bite into. More development teams have been set up. So what this has happened, this has led to a quite confusing and not so productive environment for our development teams. A slight miss from one or two developers that can carry a high possibility of complete standstill for all of the development teams. And if that starts happening more frequently, then it causes more frustration and not so good environment for the developers. So what lesson we learned that we need to separate our code base in such a fashion that we have multiple modules, or should I say services, that our dev teams are responsible for maintaining them. That can be based on the domains or based on the actions those services perform. So we decided to break our services in one monolith into multiple services so that one change in one service shouldn't affect other. Not that we want any breakage in the system, but again, if breakage happens, which is quite normal in development, it shouldn't affect other development teams, so they can function completely isolated from any other breakage. So that is probably one thing we learned, that we need to break our system monolith into various services. Now, I'm not saying we are doing it in a microservices way, but at least we are focused on the domains of those services. And to do that, we found out that our second important thing, or the second lesson, should I say, we learned that our event listener part, which I showed in the previous slide, which is responsible for handling events from the quorum, is tightly coupled to our application code. So what happened that if we need to start scaling our application services, and that event listener is tightly coupled to the quorum part, then without taking that event listener out of our application code, we can't scale out that very well. So before we start breaking our code, we need to decouple our event listener logic from our service and take it as a separate service. So we can call it a gateway service or quorum gateway service that will handle all the quorum interaction. And if we want to take it as a real microservice example, then that service might as well handle all the communication between multiple services as well. So using AMQP or RabbitMQ or Kafka, whatever technology solution we decide on it. But yeah, so for us to actually start dividing our services, we need to take our event listener code out of our application, create a separate service, and in that fashion, we can evolve and scale our different services individually. So I think that's it for my part. So Jatin, back to you.
Right. So I think I'll go through next couple of slides, just sharing some other challenges that we had more from operations angle. But I realized that we are 45 minutes into the talk now, so I'll try and be as swift as I can. So when we talked about pods, we talked about having to run the pods with all the services, and that includes the services, the database service, quorum service, API service, Rabbit service, then the web service. And then if we have to bundle all of that and we have to deploy the whole set every time for every customer, then running all the full set of services for every customer in cloud, the cost exponentially grows, right? Every customer you onboard, the cost grows. So we did optimize by having multiple offerings whereby you can have a setup where you don't get the full set of services, as in not full set of dedicated services. So you still, everyone definitely gets their own quorum nodes because there is no compromise on that aspect. That's one of the important aspects, that you get your own quorum node. But then rather than getting your own full set of database, you share your database with other customers. You share your API layer with other customers. You share your AMQP layer, that is the messaging layer, with other customer. And that kind of, significantly keeps cost under control. So this is just visualization, which gives you a visual idea of a dedicated quorum node for each customer, but other services are not dedicated for a given customer. And then there are a couple of options around that. I won't go into the details of this. Last final point that is to touch is around the monitoring of the key aspect that we monitor is quorum. And one of the ways that we do that, I didn't probably make it clear, everything that we run in cloud. So there are multiple cloud accounts. There is a cloud account for customer 1, there's a cloud account for customer 2 that has got quorum running, API running, and then there is a central monitoring account from which we use Prometheus stack to monitor. So quorum, there are a couple of good open source options that allows you to build Prometheus exporters, deploy Prometheus exporters with quorum, and that that shares the metrics that goes out to the central monitoring account, from which we have Grafana dashboards, etc., that regularly raises us. Well, when I say regularly, it used to regularly raise us alerts if any quorum were forced to drop out of the network. And as with any new technology, which still blockchain is, we had some fun and games where for no apparent reason whatsoever, a quorum node may drop out of the network and then join back into network. And unfortunately, the solution for that was to upgrade to a more stable version. So you upgrade to a more stable version and it all starts to work pretty fine. I think that should be the last slide for this evening. So I think we should be good to open for any questions. Do we have any other co-host? Do we want to just unmute everyone, or do we want to manage the chat? Okay.
We can unmute everyone if you prefer.
Okay.
So.
Okay. Do you want to do that, or should I?
Let's see.
All right. If anybody has any questions, do you mind typing in the question? Then we may be easily able to unmute you. Pedro Pablo. Okay.
Okay, can you hear me?
Yeah.
Good evening, everyone. I have a small doubt to talk with Sagar, and this is what I wrote. If the data has its privacy based on the blockchain, when we take the data from the event listener and put it in a Postgres or whatever SQL database we're using, aren't we making a leak of those privacy, because that the data would not be encrypted inside the data the SQL database, right?
So yeah, so Pedro, so on that one, point A, Vakt doesn't own the data. We do not, we are not the owners of the data. We are the controllers of the data. So Vakt, in case A doesn't own the data, and B, as Jatin has mentioned, it's a permission system, so that the database client has is not shared by any other customer. So let's say customer A owns the data. Customer B cannot come and go and query the data of the customer A. So in that case, I think it's, since a permission system, those who have the right permissions can only access the data.
So just a couple of points over here. I'll just support what Sagar has just mentioned. As I said, each of the pod runs, so there is a dedicated pod, right? Each pod runs in its own AWS account, in its own network in AWS. And the only connectivity that is there, which is the API that runs, has got privileges to connect to the database. Obviously, the other superpower is always the CI engine that does all the deployments, that can do everything to everything, because it needs to be able to upgrade stuff. But so that's one level of control. And then there is your typical process-oriented control, where all sorts of fancy break glass processes are put in place, and our security officer is always on the top of making sure that those processes are adhered to. And one of the advantages of running stuff in cloud is that you can put a lot of monitoring in place in terms of, you know, who is accessing what and who is upgrading the privileges to access. So when the controls are right and the monitoring is put in right, then that protects you from any human exposure, and then having the network and right firewalls around that database, which is basically security groups in the world of AWS, that protects you at network layer. So using those two combinations keeps the data very well secure.
Okay, great, thank you.
So I think we have a question from Steve. He's asking, why did we choose quorum over something like Hyperledger Fabric?
So I think well, one of the key premise of the option that we had, well, okay, so we had the mandate, and we still have that, and right now we run and manage the network for our customers, but we still have the flexibility of any of our customers wanting to run that exactly same pod in their own data center. So they can literally take that and run it in their data center. So at the point of selection, in terms of which blockchain technology to select, whether it's a Quorum, whether it's Corda, whether it's Hyperledger Fabric, Quorum was the most lightweight, promising, simple technology that allowed that delivered on what we want. And so far, I would say Quorum was developed by JP Morgan. Up until very recently, it was owned by JP Morgan as well. Consensus has recently bought it. So up until now, our experience with Quorum has been very good. We have had teething problems here and there, but it has always been resolved very well in time. And we keep our fingers crossed, and we continue to hope that Consensus will also provide us the same level of support. Okay, we have. Do we want to unmute Steve? Steve, did that answer your question? Oops, sorry.
Yeah. It's I guess, did you actually look at different blockchain technologies before you chose quorum, and essentially based on the fact you're using Web3j, I assume it's based on Ethereum then. So did you actually look at other blockchain technologies like Hyperledger Fabric, which is again another open source technology backed by the Linux Foundation and IBM? I was just wondering, that's all.
Yeah, so this is slightly before my time, but from whatever I understand, that there was an evaluation done between various technologies, and for various reasons, of which technical being one, quorum was selected. Since this kind of technology is a very strategic investment, there is a technical aspect, and then there are a lot of other aspects. As you realize that we are started by consortium, right? And all of the consortiums are our investors. So there is a lot of input that we get, and also if you see, a lot of stakeholder management has to be done with CTOs and technical leaders in our investing organizations, because they have got a strategic view with us in terms of where we are going, and some of the key technologies, and distributed ledger being one of the key technologies that we select. So answer is yes, and quorum was and is still the choice that we stick to.
Okay, thanks.
I think we have one question from Yuri. It's a long one, so rather we should unmute Yuri if he's still in.
Can you hear me?
Yeah. Yeah, Yuri.
So first of all, thank you so much. I really enjoy your presentation, because I mean, you guys are really paving the way of adopting the blockchain in really enterprise scale environment, and it's basically showing that is a very, very complicated reality to bring the blockchain vision for many of the blockchain enthusiasts to making it work in the enterprise environment. So yeah, the question I had, Jatin, more, to your infrastructure deployment, the discussion that, if you come and look at the customers who read somewhere about the blockchain, what they want to have their own node, they want to have their own encryption keys. They don't want network operator to have access to the data. On the other side, they want to have high availability. They want to ensure that this all maintained. And if there is any issues with an encryption, that the network operator provides them assurance that data can be always recovered, and they want always, if there are data issues, the operator to support in resolving those issues. So how do you manage this contradicting environments, delivering decentralization, giving them certain assurance, but also ensuring that you are in the control of the platform and you can provide the support the customers need to run the business? Yeah.
It's a very interesting question, and we did spend a lot of time coming up with a solution, and generic answer to that, and I can go in specific as well, but that would probably go a little bit into AWS services. But the generic answer to that is by making sure that we have right controls in place, and we have the right assurances in place, and we have the right amount of monitoring and auditing to satisfy our customers. How do we achieve all of that? Is basically a combination of services on the cloud. So we have a provisioning mechanism using CI. So all the encryption keys that are used are all automated and are generated on the fly. And the storage where the keys are kept is further encrypted. And then there is a monitoring kept on the keys that can be used to decrypt that storage. So you see the keys where we store it, that storage is encrypted, so nobody can read the key. And then the key that is used to encrypt that storage is monitored and guarded very closely, where alerts go out if there is any violation done to that key's permissions, that allows us to prove to our customers that their keys are secure, that their keys are used only by authorized process, which really is the API who and the quorum itself that needs access to those keys to decrypt data. So that's how we achieve that promise that, look, your data is safe, it's encrypted, and there are right processes and then there are right locks and keys put in place to make sure that it cannot be decrypted.
Thank you.
we have one more question from Delvin. So Delvin, you're unmuted. You can ask your question.
Yeah, I was just curious how far along in production you are with this, or how many iterations you've done in terms of actually seeing results with the users and the banks and multiple trading partners interacting with each other. And if so, have you been able to form some case studies on how much this is saving them in their, relative to their former processes?
So I'll take that. So we went live with the first market. So the way in which oil industry works is there are various markets around the world where trading happens. We started with a reasonably structured small market of North Sea, which has got a small set of big players. It's a market made up of around 20-25 participants that make up that market, and we have around 80% of the volumes in that market. So we got a good success in that market, and then we are now enhancing our platform to launch into a bit more dynamic market. So North Sea market is the market with one product, crude. We are going into barges market, which is around Amsterdam, Rotterdam region that has got multiple products, very complex pricing. So we have done one big release and then multiple iterations into that release. We release every second to fourth week, depending upon where we are in that cycle to production. And we have done various enhancements and expanded out the ecosystem as we have grown. So it's been well used. Do we have any figures in terms of efficiency gains? Not off the top of my head, and we haven't done any case studies yet. But we are looking forward to doing one after our next market launch.
Okay, so next question is from John. He said he hasn't used CQRS before. So does it mean for different read and write? Does it mean to connect to two databases all the time, or do you use an abstraction which handles all that for you? Like, okay, so CQRS, as I mentioned, John, we need, when we have two different data models. So as I mentioned, like in monoliths, what you can do is if you have different read models, then you join them and store in a materialized view. I hope you know materialized view, but it's a view that has a stateful data in it. And there's one issue with that is you don't have to do it all the time. So materialized view, you update it on some at some level, just like a cache, but it's a real table. And in case of microservices, when this is a different data model altogether, like MongoDB, then you store that, you combine all of them operation when events occur. Let's say you place an order, so an place order event happens, it goes to your read model, but it also goes to your write model, as write model and read model at the same time. So yes, you do it all the time. It depends on how you have designed your system, but based on the events, both the databases, has to go to both the databases. So that's an added complexity. And also there's a lag, there can be lag between your read and write model. So let's say you have written into your write database, which is Postgres, and we are still in the process of storing the same state to your read model. So there might be a chance when the user goes and sees the latest state, he might not be able to see that latest state because it's still in the process of writing it to the read data model. So there are different mechanisms by you can achieve it. There are different frameworks available that can do it for you. So that can take a little bit of a complexity, but these are the inherent flaws in CQRS where eventual inconsistency can occur.
Cool. I think the questions have settled. So maybe we should call it end to the presentation and the evening.
Sorry, I've got a question.
Oh, go on, sorry.
Because this is a blockchain technology, there was a slide which mentioned that blocks are mined, like.
Yeah, so that was the example which was given, like blocks are mined somewhere, but we don't do that.
Okay.
That was an example just to give you online challenge a bank application that would be doing that, but we don't do that. So in our application, Jatin has mentioned that we don't do all such things.
So how
So,
blocks are chained then?
So when you say mining, so I thought mining when all the participants are involved and they try to prove some tough challenge. So it's inherent in our blockchain, which does it for you. There is a complexity of, we call it a gas. Based on that complexity, it adds into the chain, but we don't involve multiple parties that try to compete with each other, just like in normal blockchain to mine the blocks.
So maybe just one point over there, the way in which quorum works, doesn't work around the concept of proof of work. So there is no such thing that is required that you have worked and you have solved certain complexity to be able to create a block. The consensus mechanism that we have is Raft, is what we use. That basically is around it's pretty much, I'd say, a random leader nomination. So a leader in that blockchain at a given point of time, a reader in that network at a given point of time is who has got the authority for managing the block. So that's how it works. So basically, as I said before, like there is no mining, there is no crypto that happens over here. It's essentially a pure distributed ledger technology. And up on top, there is a consensus mechanism that is implemented using Raft.
Yeah, thanks.
Okay. All right, then. Thank you all for joining from, I think in this days of lockdown, the one advantage is people can join all around the world. So I can see that there are a few colleagues and ex-colleagues joined as well. So thanks all for joining and have a good evening.
Thank you all.
Bye.
Bye all.
Thank you.
Thank you. Bye.